Welcome everybody, and we're going to have our Q&A here with Stephanie Thomas, the Vice President of Princeton Satellite Systems. We have all of your questions, lots of great questions from folks who have indicated interest in the Princeton Satellite Systems pre-launch. So we are going to start to ask those questions. Welcome, Stephanie. How are you doing?
Hey, Aaron. I'm doing pretty well. It's great to be here and to see all the interest from the public, and I'm looking forward to answering their questions.
Yeah, there's some really good questions here. And so I am excited. And again, PSS, guys, if you aren't familiar, building a direct fusion drive, which is kind of crazy and very futuristic. It feels like something out of The Expanse, but it's real. And they are building it to be able to actually, move people to Mars someday or beyond even, right? So this is exciting, far beyond, right? Very far beyond, I would hope. This is a very exciting thing. So there will be some more technical things, so bear with us, but this is the point of a Q&A. So we're going to jump right in and we're going to start asking some questions. So of here asked a question. They were asking, what does the technology development roadmap look like? And what do the potential off-ramps look like? So two-part question, tech roadmap and potential off-ramps look like.
Right. So the roadmap for the fusion reactor is a staged development plan where we build bigger and stronger or higher magnetic field machines until we reach a pilot plant. So we're currently running the PFRC-2. The next step would be a fully superconducting PFRC-3 with twice the radius. And then the next step would be a fusion demonstration PFRC-4. And that would produce actual deuterium helium-3 fusion for 100 seconds at a time, maybe longer. And then we would really be ready to build a flight prototype engine and a terrestrial commercial or engine for use on the ground. The pilot plant. So the term that the Department of Energy likes to use is a pilot plant, which is when you have a plant that would actually produce electricity. Have all the systems, so it's not just a fusion science demonstration anymore. It actually has all of the equipment to produce electricity. So that's the goal. So that's the plan for the fusion. Now, to go into space, we also have to be maturing some additional technologies. There's a lot of synergy. NASA's working on nuclear thermal engines, and so the shielding, cryogenic propellant management, and thermal management or radiators that are very lightweight are technologies that will also be required. And fortunately, NASA is already working those in parallel.
So recap, we're at PFRC 2. We're going to 3 and 4. Did you say 4 was when the pilot plant was capable, or is that like a 5 when the pilot plant roughly?
So we may be able to integrate a lot of electricity generation equipment onto PFRC-4 and get it as close to a pilot plant as possible, and that would definitely be desirable if we're able to do that, based on the funding that we have, rather than have to build an entirely separate plant. So it does come down to the money in terms of what it takes to build all the systems and maybe the time. If the goal is your fusion demonstration and it's going to take another year or two to integrate that equipment, you may constrain what you decide to do with PFRC-4. But then once you have that fusion demonstration, the goal is that the next machine would really be a reactor that could do something, that could actually produce power in an application. So our goal is to actually build fusion reactors in a factory. And there are a number of spin-off products that may come along as we're developing that fusion reactor. So a big one is the fusion power electronics. We have a separate project with ARPA-E to develop those using the new modern semiconductors materials, and all of the fusion companies developing fusion and other applications for really high reliability, high power electronics. There's a good market there. So we're going to be working on that.
When you say electronics,
yeah.
brain kind of fixated on that. You say electronics, what do you mean? High power electronics. Are you building like switches and circuit boards? What does that look like? All right.
Yeah. So we're talking circuit boards that are pumping out tens of kilowatts per board. So similar to actually like a data center where all of our data is stored now, where you have all of these, high power boards and they're cooled, with fluids, and cars, electric cars have some of the similar technology. But so with fusion technology, we're really pushing the limits on the power per chip and the thermal management. And again, especially for space, we're interested in space applications. We need to get the whole thing into a small footprint. So we're using, the best, highest power, highest voltage, smallest chips to do that. So yes, boards, circuit boards in a chassis, boards in a rack.
Yeah, crazy. Because that's stuff you don't necessarily think of, but like you mentioned, all sorts of potential customers or exit opportunities, whether that's the whole company or parts of the company, right? You can always spin things off. So interesting concept there. Okay, I'll let you continue with the other off ramps.
Yes, so the Brayton engine is the gas turbine for space, the component that's actually going to produce the electricity. And those would also have applications to other missions, whether it's auxiliary power for high power spacecraft here in Earth orbit, or with nuclear fission engines, even radioisotope engines or generators for NASA. So the Space Brayton engines are a spin-off. The low energy neutral beams that are going to inject our fusion fuel have potential, as do the hybrid superconducting coils that are going to produce our mirror magnets. So we have a particular idea for how that technology is going to work, and we could see that having additional applications. So we do see a lot of potential streams and opportunities for additional revenue streams and products.
Very cool. Yeah, because essentially, what I'm hearing, right, and I'm just rephrasing this because this may help, I don't know, but what I'm hearing is you're building a potentially whole new power grid, right?
Yeah.
Fundamentally, when you're talking about other companies, you guys aren't the only ones, right? But
correct.
That's an entirely new potential infrastructure that needs to exist on Earth, and trying to do that in space. Just inherently, you're pioneering things like you mentioned, the size of a board. You can make something massive, but if you want to do it in space for a tenth the size, it requires different innovations. So, very interesting potential little off ramps or substantial off ramps, just based on the fact that you're doing really pioneering work on a totally new technology. And there's other companies doing this as well. So very cool.
Correct.
Follow up with a question that does kind of lay into what we already talked about here. Zachary Easterling was asking, how long do you think it will take to have a prototype built? So that's a little bit more than just because different versions of prototypes like we were mentioning. And then the cost for building these prototypes. Rough estimates, I assume, but go ahead.
Right. Well, one of the reasons that fusion has always been 30 years away, or that ITER, the plant that's being built in France right now, has taken so long is because of the very complex geometry. It's a donut. There are magnets that have to go around the plasma. There are magnets going through the plasma. And the whole thing is the size of a football stadium. So it takes a very long time to design and build. I mean, just pouring the concrete has taken years for the foundation. So PFRC has a very simple geometry, and it's very small. So it's just a line of magnets. You can picture an MRI machine if you've had an MRI, and it's basically that with plasma inside instead of you and some gas turbines creating electricity. So because it is so simple and small, we expect to be able to build and test each machine in only 3 to 5 years. So, in 6 to 10 years, we could have finished PFRC4 and be building a plant that could actually produce power. So that's sort of the time frame we're looking at. You'll hear other fusion companies also, hoping to get, power on the grid maybe within 15 years. And with us in particular, our machine is really simple, really small, so we can really build it that fast. And some of the other companies also have been able to build new generations of their machine. Helium comes to mind, TAE comes to mind, in a much faster time frame than these big tokamaks, which had been mainstream fusion. So that's important. Now the costs, again, so instead of talking billions of dollars, we're talking millions of dollars. So we're anticipating about $40 million would be good for the PFRC3 program. We'd like a team of, 15 to 20 scientists and engineers. We want, a 3 to 5 year program at a private facility, fully superconducting magnets. They cost about $1 million. A PFRC4, we think, is about $100 million to $150 million program. And again, I want to contrast that with billions of dollars to build even a small tokamak. Even Commonwealth Fusion's tokamak that they're going to be building in Massachusetts is more of $1 billion program. So we're looking at about 1/10 of the cost for PFRCs.
So, with that in mind, right, let's one of the things to think about, it's gone from billions to millions, even in the hundreds of millions. That's a factor of 10 reduction. Do you foresee, and this is not part of their question, but do you foresee innovations? I mean, things that come to mind for me are advanced manufacturing and different things that are happening now where some of these potential cost reductions in superconductors or what have you. I mean, this is super theoretical and speculative to be fair, but do you see further cost reductions coming down the line potentially as well?
Well, I don't think the cost reductions are going to be on the PFRC4 program itself, but when you look at what a reactor is going to cost, 20 years from now, when we're rolling them out of the factory, the less expensive superconductors would, be really important there, because since we're a magnetic configuration, the magnets are a large part of the capital cost. So there are some new superconducting materials, magnesium diboride, magnesium boride, whatever, so MgB2. And they're looking at making low-cost MRI machines with that. That could be a material we could use in the future. It's really cheap to make. The high-temperature superconducting tapes, which some of these other fusion companies are hoping to use, and that would require building big factories and producing lots of it, which would benefit us, because if the costs come down enough, we could use that in the entire reactor and save on cooling costs, or that would just reduce the costs again for our mirror magnets. So there's definitely a lot of potential for costs to come down on the reactor. And we still need, a team and to do a lot of science and development, to actually get a fusion reactor working. I don't want to minimize the amount of effort that's going to take, but I do see a lot of things going on in the industry that will make a reactor cost less in the future.
Yeah, and this is just highlighting that this is kind of the way things evolve over time, and being one of several competitors, in the industry allows there to be some, teamwork, so to speak, where you're the rising tide. Yeah, the rising tide can float all the boats, right? In some ways, there's going to be obvious competition and things like that. But it's important to know this is, tens of millions, hundreds of millions type of project. This isn't the first space company or space companies that raise hundreds of millions on their way to building something interesting. Some are public now, right? But they're doing more traditional rockets, I should say, even though a lot of them are very innovative. So something to keep in mind, right? Like, yes, this is a lot. Are you going to raise it all at one shot? No. The chance of that, probably not. But, getting those progressive iterations going, right?
Yeah, but the private fusion industry has raised billions of dollars in the last couple years. I mean, it's crazy. And those companies are valued well over $1 billion, several of them. The Fusion Industry Association, of which we're a member, put out a nice report this summer and, summarized all the private investment. So it's definitely, that's what it's going to cost. And we know, like, the interest is there in fusion today, to solve climate change. In our case, we're looking at it to really open up the space economy and, get places faster, bring more stuff. So
very, very exciting stuff. It's a big undertaking. I don't think anyone's trying to act like it's going to be something you're going to build in your garage easily. Big undertaking. But with that, we'll jump quickly to the next question that Ryan has. Most tech startups fail as a result of technical experts failing to get support from business experts. What is your hiring plan? And when do you intend to fill critical roles such as business development, SMEs, and finance?
Yeah, so while it's true that our current PSS team is composed of technical experts, I'm an aerospace engineer, my boss is an aerospace engineer. We've also been in business for 30 years. We sell commercial software, we've done a lot of government research projects, over $1 million. So we do feel like we have some business expertise. We would definitely look to hire, more business development, marketing expertise during that PFRC3 program and getting us ready, to spin up, develop those spin-off technologies, growing that side of the team, especially that power electronics is the item that we really see as sort of the first product. So yeah, we do foresee, building a team to market those products in the near future, in the next, 1 to 3 years.
And that's part of that team that you were talking about for the 40 and 100 millions and all this other stuff.
Correct.
Right? There's development costs, but there's also building a business cost, which is the benefit of fundraising. A lot of R&D, in theory, this kind of touches a little bit on the last thing we talked about, but a lot of R&D, the thought is that you can start to use some of those costs by winning alleviate some of those costs from investors by winning grants or, whether that's DOE or NASA or others, that there's a lot of these things that need to be done. You guys have a history of winning some of those, as is on the page. So it's a good way to think about reducing some of the risks associated with investments and from an investor perspective. Great. We'll move on to the next question. Cody Peterson has asked, as scientists and engineers, there's a tendency to perfect a technology before finding a market. that strategy could deplete the runway. With the DFD, what do you imagine the first minimal viable product being? And what problem do you imagine solving for your first DFD customers? We've touched on these things a little bit, but I'd love to see maybe some more explanation there.
Yeah, so we do foresee the first product, or that minimum viable product, that first 1 megawatt reactor after PFRC4 has been a success, to be for a high value application, which hopefully space would be great, or a military application, or a government application for a critical power need. A niche application where we're not competing on cost per kilowatt, because as I said, we anticipate it's going to take some more time to develop a manufacturing processes and get the costs of a commercial reactor down. So we're looking for a high value first application. So, the problems solving for our first customers, well, for space, I think, we wrote in the pitch, we want to get to Mars faster and bring more with us. And that's definitely on everybody's mind, and it's a goal of NASA's, and we need to get the people there faster so they spend less time in space, so they have less radiation during their trip. And then they have enough power for the base to really be functional when they get there. And also, we want to discover life on the outer planets. And so we want to get more equipment there, get it there faster, and learn a lot more about our solar system. And then we want to open the space economy, as I said, and start industrializing space and using those resources. So any of those customers, I think, could be the first customer of a space reactor, the Mars mission, or potentially even a commercial application. People are building space stations in orbit now, commercial space stations, and they could also benefit from a fusion reactor, as opposed to, relying on solar power, which are actually really big and still fairly expensive.
And then, not to mention what we've talked about before, does touch a little bit on this. There's potential off ramps, right? So even if the DFD is still going to take, as a minimum viable product, the DFD is still going to take quite a bit to get to. You will be able to have customers that can support potentially, right, on things like your ultra high power electronics and things like that, right? Where these off ramps start to provide some risk reduction as far as revenue. You're not betting it all on just, one DFD thing customer, and that's your first revenue coming in. So the question is solid, right? Like, are you just going to, tweak a little wrench for the next 30 years because it's not quite perfect, right? Makes total sense. There's a lot of off ramps that we mentioned before. Very, very good question. Shifting a little gears a little bit here. John Robinson asked, how closely do you work with NASA? And are there any companies you think you will work with or team up with in the future?
Yeah, so NASA actually gave us our first contract to really work on the design of the space engine when we won our NIAC in 2016. That's NASA's Innovative Advanced Concepts Program. And we do keep closely in touch with various engineers in the NASA hierarchy and at the STMD, Space Technology and Mission Directorate. So they're certainly aware of our work, and they've had requests for information that we've responded to. Now, fusion isn't quite on their roadmap for NASA. For them, it's still an aspirational technology where they know they want it, and they would love to be able to buy it if we had it ready now. But at the moment, they're a little focused on their fission technology, but we are keeping them in the loop. And we would anticipate that they might have programs in the future, as you mentioned, grants, public-private partnerships that we could apply for, and then we could be working together on this, once we have some more results with the next machine. We know they're interested. And additionally, we anticipate building a factory and creating PFRCs, but to integrate a fusion reactor onto a spaceship is actually, again, a very large undertaking. And we would anticipate partnering with one of the big aerospace primes. And we've been in conversations with, for example, Northrop Grumman, Lockheed Martin, and they are potentially interested. So we would definitely see, a partnership. We are a small company, and we would benefit from their expertise.
Absolutely. And then a follow-up, coming from someone else, but very similar along these lines, do you ever anticipate a collaboration with someone like SpaceX?
I'd say SpaceX has their path, that they've chosen to follow, and, they're building their technology, they're confident that it will get them where they want to go. I would argue getting there faster would highly be worthwhile. And again, if we were successful, if PFRC3 is very successful, I could see potentially them, partnering with us in the future or being interested in purchasing a fusion reactor. But certainly at the current time, we haven't been working with them.
Yes, SpaceX is the big one in the room, but yeah, their current tech roadmap doesn't have a spot for fusion. Which let's be clear and frank here, right? Fusion is the reason people are investing so much into it and excited about it is because of the potential, but it's not there. It's not rolling off the line tomorrow kind of thing. So someone that's building a lot of business roadmaps, especially large businesses that are raising lots more money from investors, I don't know the last amount of money they raised, but someone doing that isn't saying, hey, we need something that we can't buy today. They're hoping they're relatively easy to plan for. So, there's reasons, right? This isn't like, we're not just pretending this is all magical kind of thing. So makes total sense there. Let's see, we've got Leighton asking a question as well. PSS has a novel concept for deep space propulsion, but what is the plan for commercialization? Who on the team has experience with commercializing deep tech? This kind of touches a little bit what we talked about before, but worth diving in a little bit deeper.
Yeah, and again, we're not a one-shot company. Again, we've been in business 30 years, and our expertise is in satellite attitude control, orbit control, navigation, and we actually have an extensive SBIR history. We've executed SBIRs in formation flying, solar sails, precision attitude control, and we have other technology that we're still working to develop and flight test, such as our own reaction wheel and our optical navigation with neural nets for terrain navigation. And so, for example, we have applications in NASA has a tipping point program, another one of these public-private partnerships, and we have 2 applications in there to advance some of this other technology. So our plan is, not to just build fusion reactors, but to continue with our existing, aerospace work and continue with our services and build those other products. So we spoke about the fusion spin-offs, but we also have, our aerospace technology. And for example, we're known in the solar sail community for our solar sail simulation capabilities. NEA Scout, which we did some work for, is going to be launching in a week or 2. So we're going to keep working all those eggs in our basket. So I'd say we actually have experience commercializing, deep tech in our software and in our, consulting services, that we work with, for example, NASA on providing third-party analyses of some of their programs.
And hence the name Princeton Satellite Systems, not just Princeton Fusion Systems or something, right? So lots of opportunities for commercialization, good experience, always room to grow as part of the roadmap, bringing more people in, as you mentioned before, to help with that. Because, you can always do better, right? So it makes total sense. Let's see here. We got a couple of questions that are similar. So we'll kind of combine those two. Brandon and Larry have asked a very similar question, asking, what does your anticipated growth look like in the next 3 to 5 years? I guess we kind of already touched on technology. Maybe there's a different way to answer that, or a little bit of both.
Well, I mentioned, so we're a small group of, 4 or 5 engineers right now. We probably want a staff of at least 15 for developing PFRC3, and we need scientists, engineers, technicians, business development, staff in a variety of categories. So that's staff growth. And in terms of, revenue, again, we're looking to mostly pursue public-private partnerships for developing this space technology and this reactor technology for flight, because it's very expensive, and that's why NASA has these tipping point programs where they can match that private investment, with government dollars to offset the cost for the investors. So that's the plan for providing the funding to keep going. And then in terms of the revenues, again, we discussed we have commercial consulting services, we have software, and then we're looking for these spin-offs with the fusion power electronics, probably positioned to be the first to bring in significant revenue. That's a new product line.
Very cool. Lots of opportunity for growth, even if fusion isn't sitting there, in 2 years.
Even if it takes longer than expected,
right?
Everybody's going to need boards. So.
Exactly, right? Especially as they're all trying to solve it with their billions of invested dollars, right? So we have a couple more questions here. Rodney's asking the opportunity to invest. When is that going to open up? Is it already open? And if not, when? And then George is asking, hey, I only have $500 to invest. Will you accept me as an investor?
All right, so yes, George, we would welcome you as an investor. The minimum investment in our round is going to be $150. So, by all means, you can join us at $500 and you'd be most welcome.
Yeah, so keep in mind the Stephanie and the PSS team, they're in a kind of this testing the waters kind of state. And when she said 150, that's intended, right? So just keep in mind there's room for movement and things like that. But the benefit of the technology and working with the Space Ventures team and things is that they can have really, really small check sizes and aggregate them together in a really interesting way. So yes, the intention is to be as accessible as possible. They are in a test the water state, and what that means for pre-launch, that means they're really gathering that interest now. And what Space Ventures does, we gather that interest for everyone that has signed up and said they're indicating interest. And then we let you guys know first when that deal goes out and when it's there. So you'll be the first to know when it's live and actually taking real dollars in as an investor, so that you won't miss out, or I don't know, if crazy buzz happens, you won't be the last to know. So you'll be one of the first to know if you are signing up as an indication of interest on this pre-launch deal. So that's the way that functionally works. That's the way, kind of technically this whole thing works. They're testing the waters. They're not taking any dollars yet. When they can and when they finalize all their filings, which can take a little bit of time, looks like maybe a month or a little bit more, but don't quote us on that timeline. It's coming. But when those filings are done and everything is appropriate and legally acceptable, then they will be willing to take that, and you'll be the first to know. There, a little bit long-winded answer to that question, but sometimes you have to when there's regulatory stuff involved. All right, so with that, I think we have time for one fun question coming from one of our industrial or investment advisory group. His name's Jeff Peachman, so I'm going to bring him up. He's going to ask his question here. So we have our guest here who's going to ask a question. His name's Jeff Peachman. He's part of our advisory committee. He is former SpaceX, got a lot of cool stuff going on. I'm going to bring him up. He's going to ask you a question, and Stephanie will let you run with it. We're going to bring him up right now.
Significant energy is needed to get a fusion reactor started. Can you talk about the system which supplies this energy and what fraction of the vehicle mass it will require? As a follow-up question, is the plan to start this reactor once and run it for an entire mission lasting years? How do you expect the reliability of such a system to compare against traditional space power and propulsion systems, given the complexity of the reactor?
Great. So I love the question about startup, because that's actually something we have a patent on, one of our granted patents. The great thing about the PFRC and starting it up is because it's so small, you actually don't need a separate fission reactor just to start it up the way you do with some of these larger reactors designs that have been studied in the literature. We only need a pretty small auxiliary power unit, or a little combustion unit, so we can use some of our deuterium and a few kilograms of oxygen and run this little engine for about 10 minutes and generate enough power to charge our magnets and get the plasma going. So it's actually a pretty small component. And then for another 50 to 100 kilograms, you can add an electrolysis unit and actually break down that water and recharge your oxygen and be able to start it up again. On a big mission, like a Mars mission, if you might have 6 reactors, you would probably only need to do that at the beginning, and then you could always use one reactor to start up another if you had to take one down during the mission. So if we have only 100 kilograms or 150 kilograms out of a 10-ton mission, the startup mass is actually very small. So great question. Yes, so we do turn the reactor on, and it's on the whole time. It's a continuous thrust type of trajectory, and that's how you end up with basically these straight line or rectilinear trajectories. And it's just like Robert Heinlein's books, where the engine is on and there's pretty much a switch point halfway when you turn the engine over, and then you decelerate the rest of the way. So we have to launch the reactor from the ground, and then once it's in orbit, we turn it on using our auxiliary power unit, and then we go. We also think it's possible that if you're using a PFRC in rocket mode, in direct fusion drive mode, you might be able to actually close off that reactor, have some vanes that come in and convert it to a closed loop reactor when you get there, or you might have ones that are dedicated for rocket usage or dedicated for being used in a planetary surface power. So I think, oh, and the other big part of that question was reliability. So while the reactor sounds really complicated, a lot of it has no moving parts. So the magnets have no moving parts, the heating system has no moving parts. The key components that have reliability considerations are the electronics from radiation, and that's a general lifetime, it requires shielding. But the cryocoolers for the magnets have moving parts, and so would the turbines generating power. But these are components that we know a lot about, right? How many, rotating machines do we have? Every airplane engine is an example of a rotating machine, and we know a lot about how to keep them reliable. We certainly need to design for reliability in space, but for example, for a planetary surface reactor, you can envision doing some maintenance on those turbines every 5 years and having your reactor go for 30 years. And there are cryocoolers that have been operating in space for over 10 years. So we do know how to build highly reliable systems, such as those what we will require.
Very cool. I'm going to just be quite upfront. Like most of the stuff you talked about, a little bit over my head, but
Okay.
Hopefully the technical folks out there, again, Jeff comes from SpaceX, 10 years at SpaceX, did a lot of building for them on Starlink and the landing legs for the Falcon 9 and just a lot of cool stuff. So I love listening to you guys talk and just hearing a little bit about that. So, to be fair,
All right. Well, yeah.
I'm sure some of us.
Yeah.
Yeah.
Mass,
Go ahead. Yeah. Dumb it down for me.
Right. What do the spacecraft engineers care about? Mass, reliability, because we can't fix things once they're in space, and then, power. So, right. What does it take to start up a 1 megawatt? That's a lot of power, but it turns out it's a small amount of mass. So it does all work out. And yeah, as a space engineer, he had great questions.
Yes. And he'll go deep. And so we're going to have another question. He's got 2 more for us. So we're going to go ahead and drop another one in here. And hopefully we'll get that up here in a couple of seconds. Give me 1 second to put that up.
Over the past 60 years, a large fraction of the funding for fusion research has gone into developing tokamaks. As tokamak plasmas became hotter and denser, and confinement times became longer, researchers discovered more and more plasma instabilities. They needed to solve issues related to those instabilities to continue raising their triple product. Can you comment on whether you expect development of your reactor to be more or less susceptible to such instabilities, and why?
So that's a good question. I'm going to dumb it down in my language, right? All of the power that we're trying to get is kind of surprising some folks with more instability that they're trying to correct for. What is your guys' kind of thoughts on that, and how does your design potentially help or not? All those questions.
Yeah, so I talked a little about tokamaks earlier and how, they are very complex geometry and how, developing them, is taking all of these years, to build each machine iteration, right? Because they're very complicated. FRCs, and so a lot of people, like the public, might know about tokamaks because that's where all the money's been going, because early on they showed a lot of promise of, like, in the 60s, it looked like tokamaks were going to be the way to go. FRCs, which is a field reversed configuration or a little self-contained plasma ball, have fundamentally different magnetic structure than tokamaks. So some of these disruptions, that you've read about, there was a disruption that actually lifted the 20-ton jet vacuum vessel several inches off the floor, and the stored energy in that large tokamak would be enough to lift it several meters. The FRC cannot have those types of instabilities because it doesn't have that toroidal magnetic field. So there's a whole class of disruptions and instabilities we don't have to worry about. There are a few instabilities, the tilt instability, which could affect FRCs, but the growth, and that's the whole FRC kind of tilting and rotating like this. One of the ways we slow that down is by having a long FRC. And if you look at our pictures, it's not a little round ball, it's long. And that's one of the reasons it's long, is that helps keep it stable. And it's also minimized by what we call the kinetic nature of our plasma. So tokamaks are like a fluid. It's like water, and things that happen in one part of the wave go around the tokamak and affect the other part of the wave. And it's a feedback loop that causes these disruptions. The FRC doesn't work that way. The particles are really operating independently. We call it collisional. It's just like a billiard ball, one particle and another particle. And so those types of instabilities don't propagate. So not something we need to worry about. And, always, once we deal with burning plasma and high plasmas, yes, there's always the possibility that there's some behavior that we didn't predict, that we then have to deal with. But again, because the energy in our plasma is so low, like it's not going to blow a hole in our vacuum vessel. That's just not going to happen. So that's a good part about making a smaller reactor.
Very cool. Now, that is something I feel like I could follow. So I'm hoping most of everyone else could follow that. Very, very interesting, just with like different geometries, how that can impact and just make it fundamentally so you don't have to deal with the problems of more complex geometries. When we think about physics, geometry plays a big role. So this is an interesting one here. One last question that we have from Jeff, and I'm going to bring that up right now.
I have a question about the helium-3 supply. So helium-3 is a very rare fuel, and the USA produces roughly 10,000 liters per year, which works out to about 1.3 kilograms. You have proposed some missions which require a fraction of a kilogram of helium-3, and these missions would give us very valuable science and would be a great use of the strategic resource, in my opinion. However, you also cite military and industrial customers as the majority of your target market and propose building 30 reactors per year at 10 megawatt electric each. This would be a total capacity of 300 megawatts electric, which should require roughly 15 kilograms of helium-3 per year. Can you comment on how the helium-3 supply may affect your future business plans and how the supply can be realistically increased in the near term? Thank you.
So that's a great question. He did some math there if you weren't following along, right? Like we're only producing 1.3 kilograms of helium-3 a year. Is that the rough math? But some of the stuff, if you want to send large masses with your system or any fusion, using a lot of different fusion systems, using helium-3, we need to produce 10 times that or 100 times that, maybe, who knows, right? So we maybe talk a little bit about that, the dependence on helium-3 or not dependence, whatever, right? Just talk a little bit about that, the helium-3 supply and how that affects you.
Yeah, I loved how he actually did some calculations, and we've usually used the number of 100 megawatts per year as a number that can probably be sustained with helium-3 that you buy off the shelf today. But an important point is that while helium-3 is rare and scarce, it actually exists. It exists in nature, and it's a stable isotope. So it exists on the moon, it exists in the atmosphere of the outer gas giants, Uranus and Neptune, and it exists in Earth's atmosphere as well, although it wouldn't be economical to get it out of our atmosphere. Contrast that with tritium, which is the fusion fuel that is easier to burn, as in it requires a lower temperature, but it does not exist in nature. And when it does exist, it's highly radioactive. So it has to be bred within a reactor, which requires lithium and lithium-lead mixtures and requires your fusion reactor to actually be a tritium plant in addition to being a fusion reactor. So by choosing helium-3, there's a lot of benefits, which is, we can go out and get it. We can make more than we are currently today on Earth from natural gas extraction, from CANDU heavy reactors. We can breed it. So one of the things that us and other fusion companies have put forward is you can have breeder reactors or deuterium-deuterium reactors that create tritium, which then creates more helium-3. So it would be possible to create a stream on the Earth. And we could probably be not cost competitive with solar and batteries with that, but certainly there would be a lot of places on Earth where that could be cost competitive, where you don't have a grid, where you need power. So breeder reactors are a solution on the Earth. Now, if our DFD rocket is successful, that would enable going and getting helium-3 from the outer planets. So if we're looking long term from now, 50 years, 100 years, I definitely foresee, getting helium-3 out in the solar system. And that could be even cheaper than breeding it. And then we don't have to have DD reactors, which are more radioactive. So then we're producing even less radioactive waste, and we're actually just getting helium-3 where it exists. So again, the benefit of being a small reactor with regards to helium-3 is in order to test our reactor for development, the helium-3 exists. We can buy it off the shelf. We need a tiny fraction of that 1.3 kilograms for testing purposes on a PFRC-4. Whereas, for a big tokamak to test with tritium, like they're going to have to create that tritium to even run the tests in their reactor. And where's it going to come from? So they have a lot of challenges there.
Very interesting.
Yeah.
And it says a couple of fundamental things. One is like, right, thinking about the fact that we can create more as needed, right? This isn't like new, now you have to think about new science, chemical science or something like that to make something new.
Right.
It exists, right? So we know how to do it. We can do more. Again, this is the rising tide, all boats kind of thing. There's opportunity with the industry at large wanting to do this. And then, so that's kind of the shorter term. And then I like to think in decades and, potentially even centuries sometimes, but, and I want that to be faster, but even so, like, I don't like your 50 to 100 years. I want that to be 30 years, but I'm making that, I want to make that happen. But there's opportunities in our solar system, which feel really far away. But
but I mean, the moon is right here, right? The moon, it takes 4 days to get to the moon, maybe less. And we have been in contact with companies that are working to build infrastructure to mine the helium-3 on the moon. And we've signed an MOU with one company that, we could buy the helium-3 if they're successful in creating, again, that space economy, that resource is there on the moon. And it could definitely be economical once we have a working reactor. And again, potentially, Helion is also interested in burning helium-3 in their reactors. Again, it's less radioactivity. It's the goal. It's a better fusion reaction to be going for. But the moon is right there, and we do see that could be 20 years. We could be burning helium-3 from the moon in 20 years. I think that could be definitely feasible.
Well, see, that's what gets me excited, right?
Yeah.
The idea that no one's saying this is easy, right? But sometimes it takes people really pushing that envelope, and that's what I view you guys are, getting excited about pushing the envelope and not relying on someone else to invent this 50 years or figure out the problem, how to solve these problems 50 years from now, solving them now and moving things faster. Because I think, if we want to see the future happen sooner, we want to own a piece of that future, this is the way of doing it. So it gets exciting, right, when you think about that. Of course, there are incredible amounts of risks, 100,000 different ways you can fail. And just, crossing the street can be a failure sometimes. So, with that in mind, I think that this is incredibly exciting stuff. Does feel like the future to me, at least. But thanks for taking the time to answer some of these questions, and hopefully it's helpful as people are making their decisions on where they may want to invest in the future. But anything you want to add? So
it's interesting that helium-3 mining from the moon has featured in several movies and the new TV series. We were just watching For All Mankind on Apple TV, and helium-3 fusion actually featured prominently in that show. And in that, fictional timeline, NASA was actually profiting financially from the helium-3 on the moon. China has cited helium-3 on the moon as the reasons that they put their lander, where they did. And don't there's helium-3 on the moon. And then the movie Moon featured helium-3 mining, and they actually depicted the sort of tractor thing that was driving around and chopping up the regolith and shooting the helium-3 back to Earth. So it's in the media. Another point I like to make about fusion in general is that you need a physics path to creating, net power, net Q. Everybody is conscious of that, but you also need an engineering path. Are you going to be able to build it? Like I said, are you going to be able to fuel it? And then eventually, is it going to be economical to do so? So, from a materials perspective, from a fuel perspective, and that's one of the reasons that the PFRC design, the reason we've designed it the way we have, is with a focus on engineering feasibility and choosing a fuel that exists and choosing a fuel that solves radiation problems, so we don't have a materials problem at our wall, and so that it's something we can realistically build in the near future.
And that's an incredible point, right? And I'll also mention that the engineering thing is an incredible point. I'll also mention that if anyone hasn't seen For All Mankind, they should watch it, because this doesn't feel, I mean, I'm not the engineer, but or the scientist. I don't think any of these things, I think they put a lot of effort into trying to look like what a realistic, semi-realistic timeline could have looked like. In the science and engineering that they did were all relatively realistic within, known physics and science today and engineering capabilities. So, it is something that gives me, some excitement for what the future could look like, because that they were going to Mars in the 90s in that timeline or something. I don't know what
that was NASA's plan. Yeah. Before everything got canceled, that was the plan, right? And then the Cold War ended and everything got canceled. But 100%, that was NASA's goal back then. And so now it's still our goal today.
So, I mean, it's exciting. And I think that, you know, it's cool to be a part of it. Honestly, quite frankly, it's an exciting thing to be a part of. Getting an opportunity to make it happen, it can be quite powerful and empowering. So thank you for, you know, taking the time to answer some of these questions. Did you have any other final things you wanted to impart?
I should just say that, you know, it's great to be here, and it's wonderful to be a part of your platform and to be meeting people who are as excited about space and space development as we are. And, you know, working on fusion, I feel for me is one of the most impactful things I've worked on in my career because of the potential to help with climate change and global warming and solve power problems. So we have a technology here that could do, you know, the things that I grew up wanting to do in space, you know, travel around the planets and also solve problems here on Earth. So it's a really, really exciting thing to be working on. And
I agree.
I look forward to, you know, continuing the work.
Awesome. Well, I appreciate the time, and we will let everyone go and, you know, drop any questions or what have you, continue it into the discussion section if you have them.
Wonderful.